So now this y prime is your derivative of that circle function at the coordinate xy. Now we can check to see if this actually matches what we would have done explicitly with the f of x function. So there's my, or in this case g of x, so there's my g of x function. So I'm going to differentiate my g of x function, so d by dx. So this is just a check to see that these actually match. D by dx of g of x is equal to 1 over 2 square root, so there's my outside function, 25 minus x squared. And then I'm going to apply the chain rule here. So the inside function is negative 25 minus x squared, so I'm going to get negative 2x. Simplifying that, the 2's cancel, so I end up with negative x. Well, that matches a negative x there. And in the denominator, I'm left with this expression, 25 minus x squared. Now, these are in fact actually exactly the same, because if you look at how we defined the y function was defined as, where is it here? Square root, there it is there, square root 25 minus x squared. So these in fact are equivalent expressions. One is in the explicit form here, this is what we've been doing, and here this is in the implicit form. So we differentiated implicitly, simplified and solved for y prime, and we get this implicit derivative in terms of x and y. So there's a bit of a disadvantage in that it's in terms of x and y, so you need both the x and y coordinate, but it is this is what we are going to be moving towards, because really in some ways we can look at things as everything as implicitly differentiated, which I will get to a little bit later. So let's try a couple of these. Okay, we can verify this one again. This is the same function. Okay, this is when g of x is square root 25 minus x squared, or x squared plus y squared equals 25. So when we take a look at it, then I'll do it differentiated again. So we have x squared plus y squared equals 25. The steps were differentiate the x normally, differentiate the y normally, but every time we hit a y, we need to differentiate the inside function, which generates our dy by dx. Okay, and that's our derivative expression. We want the change in y over the change in x. So solving for dy by dx, which we did above, we get negative x, and then we divide negative 2x divided by 2y, so we're going to get negative x over y. So if we take a look at our circle here, this is our circle with x squared plus y squared equals 25. This point here, I picked this point specifically because this is kind of a familiar point to us. This is the point right at 45 degrees. Okay, so if you think, imagine a tangent line through there. So I'm going to draw my tangent line through there. We probably can see just visually that that slope really is, okay, I'm just going to write my 45 degrees in there, and we can see that that tangent line slope really should be negative 1. So the point is defined by x equals 5 over root 2, y is equal to 5 over root 2. So when I actually plug in my x and y into my derivative, okay, when x is 5 over root 2, y is 5 over root 2, I'm going to get negative 5 over root 2 divided by 5 over root 2. The slope is negative 1. Okay, and that is consistent with what we see over here. Okay, so the slope does work. The other one question was asking, calculate the slope at this coordinate, 0, 5. Okay, 0, 5, you can see there's a horizontal tangent there, so we should end up with a slope of 0. So if I plug in, and I'm going to use my dy by dx, oops, what happened to my, there we go, okay, so if I use my derivative expression, so dy by dx at 0, x is 0, y is 5, I plug it into my derivative expression, there's my negative x over y, and I get a slope of 0. Okay, and notice that that is consistent with that coordinate there at 0, 5.